Welcome back, everybody. We're back to the last two sessions of the day. First one led by Miguel and Pedro on the Mojaloop performance, scalability, and architecture update. Miguel and Pedro, take it away.
Hello, everyone. Let me just prepare my slides. Thank you, Simeon. Hello, everyone. My name is Pedro Barreto. I'm an architect at Crosslake, and I've been working with Mojaloop on and off for the last 2 years now, mostly focusing on the performance and the scalability aspects of the open source software. And I've been working with Miguel for the last 3 PIs on the scalability and performance POC that aims to deliver the next generation architecture for Mojaloop. So mid-last PI, we kicked off this POC initiative, which started as a way to anticipate the next level of scalability and performance. It has a second important objective, bringing down the cost for the initial deployment and understanding how much each scaling step represents in terms of cost. The last but not the least important objective was about learning which patterns and principles can be applied to the rest of the Mojaloop software. So this exercise was focused on the central ledger components as they have the biggest impact on the switch's ability to perform and process transfers quickly and at scale. We'll now quickly go through a few slides to refresh the context. These were the high-level technical objectives we have established to begin with. Redesigning transfers and participants interactions using a distributed transaction model, building distributed event-based transactions based on the single responsibility principle and microservices, and implementing event sourcing in CQRS. To recap what all that means, the focus of this exercise is the central ledger. So we started by splitting the transfers and the participants into dedicated services so that they can do their own things really well, and then designed the whole transaction as a series of messages being passed between them. When we then proceeded to building that more granular event-driven transaction flow, applying single responsibility microservices for participants and transfers, which are actually clueless about each other and only communicate through events. We tested all of this to see if the system was scaling and performance well. Before proceeding, it actually did. It would perform really well. Finally, we built the event sourcing mechanisms and the CQRS read projections. Again, load testing these mechanisms to make sure everything was still scaling and performing. And it did. Since we start, we've been heading milestones as we progress. The first milestones were to establish scalability of the central ledger, built according to the guiding principles, which were the pure event-driven microservice design that had no shared data, where all central ledger components own and hide their own data, and communicate exclusively by events without database controlled transactions. The second milestone was to investigate other principles like CQRS, event sourcing, and these two in conjunction would allow us to send messages to Kafka that signal a complete task and carry the state that will trigger the creation of a set of projections or views on the read part of the system. These patterns are obviously not new. They're extensively used in other distributed systems such as Amazon and LinkedIn, and they have obvious advantages in terms of scalability. They do come with added complexity. The objective of the second milestone was to prototype them and understand where and how we could have some benefits from these patterns. We have achieved the first 3 milestones until last December, when we released the first draft version of the report out document, with all of the details of how the POC is built, including the list of things that need attention to make it production ready. This has been available since then. The last milestone is making this production ready, which obviously requires some work. Okay, so last convening, we bragged about how we managed to achieve 6,000 requests per second end-to-end, but we had so many great results about how it scaled almost linearly and in a cost-effective way that we didn't manage to have enough time to fully explain how all of the details of how this works. So don't get me wrong, we once again made this go a bit faster, but we like to spend some time explaining the details of how this actually works. and the patterns behind it. The first two principles were applied. The single responsibility principle, which is basically the art of making something do one thing really well and not try to solve all the problems at the same time. And the second was the strict microservices that enable the separation of both logic and data. We can see how we went from an already existing degree of logic separation with the existing code, the legacy code, and to the new way of doing, which is obviously everything is actually separated. It's not only the logic that's separated, it's the data that's separated. And actually the logic is separated in a slightly different way. There's this famous sentence by Eric Evans, who wrote the domain-driven design book, from which we base some of the principles, making the point that signaling to the rest of the application that something happened on one part of it is of major significance. But what exactly is event-driven, and how many flavors are there? To start with, an event can be described as a message that transmits the knowledge that something happened in the past, thus is immutable. To better appreciate why event-driven architecture is so good, we'll go through a few inter-service communication examples in the next few slides. A fundamental aspect that splits the many styles is how the correct sequence of actions and events is achieved. There are two main styles. It's the orchestrated style or the choreographed style. We'll go through them. This is the first example. This is the God pattern, the God service pattern, where one service rules them all. You can see that service A knows it all. It has all of the flow control logic, and all services are very focused on doing their own thing. This approach is fine, but it tends to, over time, move more and more responsibility to service A, effectively reducing the benefits of service-oriented architecture and increasing the complexity of service A to the point where the benefits are gone. This is another example. This is the process manager, and it's not too different from the God service, but at least here, there was a conscious decision of making one single process the one that knows it all. Obviously, the same drawbacks still apply. The main process is incredibly rich and has a lot of logic, is highly complex, and the other services tend to be very thin and very, they don't do a lot of the control. This is the mesh. It's quite fashionable a few years back, or was, well, still is in some places. And in this way of doing things, all services know about every other service that it needs. It also has to know, obviously, how to talk to those other services that it needs. Of course, this knowledge increases the complexity of each individual service. Over time, there's a tendency to create a complex and unmanageable web of dependencies. And this is typically called the distributed monolith pattern, where we don't fix the dependency issue. Sometimes we actually increase it, the typical dependency issue that we have in a good old-fashioned monolith, but we actually add the complexity of distributed systems. So when most of the times this is not really well implemented, and it ends up being worse than a good old-fashioned monolith. This is the famous enterprise service bus, a favorite of dated enterprise architecture departments. This one starts as a place to have routing and messaging translation decisions, which is typically called the messaging middleware. Paradoxically, this pattern typically ends up sucking all the logic from the multiple services and putting it in the single ESP. And this is one of the best examples of what constitutes an anti-pattern. It's supposed to be lightweight and connect all of the services that do the job, but it actually ends up centralizing everything in an odd and expensive technology. It's quite the opposite of what we actually want. We want smart services and dumb pipes. This is a very try to be smart pipe and very dumb services, which have not a lot of logic. So unless you're selling them, never use this kind of pattern. We can see what all these patterns have in common. There's always some big component that knows all of the flow of the application and knows how to orchestrate everything. This is why it's called the orchestration. There's always a maestro. There's always someone or some component that knows the flow. This is the choreography, a different way. And we can see how it differs from the orchestrated style. Here, services know only to do their work. They have no clue about the other services. They are reactive. All services know is how to react when a certain event is seen. And this means for some events, I will have to do some work and then output some result of work as an event again, so that the other services can try to listen to those events and do the same. This is the typical pattern, the pub, sub, or publisher subscriber pattern, which is not exactly the same as the observer pattern. The fundamental difference is that in the observer pattern, the listener knows the observer. And in this case, the publisher and the subscriber, they have no idea of each other. The subscriber only knows that it's interested in subscribing some types of messages, and that's it. So the big advantage of this style, choreography versus orchestrated, is that everything is async. That's the first one. This is not exclusive to this style, but it adds to it. The sender does not need to know the receiver, which is a major distinction. It doesn't even rely on the other service's availability. Maybe the other service is not there, or it's busy. It's going to come back a few milliseconds or a few seconds later, so I don't have to wait. This means that the receiver or the subscriber can take its time and can eventually come back later, not having to leave the sender hanging in line. This is important. It decouples time, it decouples calls over time, which is contrary to what typically RFC or our RPC does. An even better benefit in the context of large scaling systems, we can scale all of them individually, which means that some of the parts of the system that will be hit a lot, we can scale them by a lot, providing a lot of resources and a lot of instances. The other parts can be smaller as they need less resources. Obviously, this is the pattern that we chose for the POC. It's the choreographed with event-driven. Well, in this slide, you can see the representation of the flow. This is the flow between the transfers and the participants. It looks like both sides are having a dialogue, which is kind of contradictory to what I just said. In reality, transfers and participant accounts are not talking to each other. They have no clue the other side is there. What they are doing is really just listening to events and shouting back that they have done something as a reaction. They don't know. This is quite important because we now can code the two sides in a much more simple way. And this has profound implications in the complexity of our code. Here you can see the whole thing. We can see the overall flow that we have implemented in this POC. It represents what's happening inside the central ledger for the life cycle of a transfer. On the top of the prepare leg, on the top we have the prepare leg, and on the bottom we have the fulfill leg of the transfer. This dance of events that trigger a reaction on another service is actually quite fast. When for some reason one service encounters an error, all it has to do is to send an event signaling that something went wrong. The other services will react to that message, to that event, by doing whatever cleanup tasks they have to do on their tasks, on their side, if necessary. So when we peek inside each individual subsystem or area, we have two main components in the design that we have implemented. We have an event handler that is coded to listen to interesting events from the outside, and when necessary, translating those into private command messages that request a business logic execution. And then we have another component, which is the command processor that listens to the commands, loads the state of the entity in memory, executes the business logic, making sure all invariants are applied, and publishes the resulting events. This decoupling is intentional, and it serves a few important purposes. These different parts have different resource needs and can be scaled independently. They can even be implemented in different languages or technologies as we see fit. And only the command processor has the valuable domain code, the code where the business rules are expressed. The ability to contain and protect that domain code and to decouple it from the triggering event and the technology is actually a fundamental aspect to ensure future maintainability and extensibility of our platform. As you can see, every subsystem here participates in this choreography by reacting to interesting events. They do their part, and then they inform everyone else of the outcome through more events. And that's how it works. Okay, so on to another architecture style that we've been taking advantage of, and this is event sourcing. It's essentially a different way of managing the state of a system, capturing all changes as events. What happens is that the application no longer changes directly some column of a database row. Instead, the state of a system is given by the events that led to that state. Those events can never be modified once emitted, and they are stored in a happen-only storage called the event store. This is akin to the mantra of accountants don't use pencils. You just write, you don't change, and then you write something else. And this is great for traceability. The effect of this at scale is massive because we only add more events. It's an happen-only system, as I mentioned, that doesn't require the dreaded read, modify, write cycle or any kind of database locks, which both increase greatly or reduce greatly the performance at scale. So in this example, we show the life cycle of the participant account entity state from creation to the last event. It's not very original because it only has 2 types or 3 types of events, but if we want to know the current state of the event, of the system, all we have to know is apply all of those events from the beginning to the end in a sequence. At any time, we can reconstruct the state up to a given point in time. It will always be correct, and the context and the intention is never lost. We know exactly what happened when the state changed. Because we carefully model our event names to reflect what happens on a business level, we don't need to infer why a certain field on a record was changed. As mentioned, this is great for auditing, but also facilitates streaming AI behavior analysis like FRM or other complex financial analysis that requires statistical models to do a lot of guessing of what happened in the system to arrive at a certain state. This enables us to remove all of that guessing. We know exactly what happened in the system and what exactly was the intention of the change that triggered the change. As mentioned, this is happen only. There is no way to edit an event. For that, we use another event, one with the effect of reversing to the previous state. So for example, a debit to fix a credit, or a rename to fix a previous rename that had a bad spelling. So this is the way we normally fix the state. We issue another state, a corrective event that changes the state again. Another important aspect is to design all actions to be idempotent, ensuring that even if we see the same messages multiple times, we are able to either ignore them or at least produce the same result, not affecting the state of the application. Now, imagine that we have thousands or millions of events and have to reload the state because of an application restart. That doesn't sound really smart, right? Because we'll have to apply them all in sequence, and that's probably going to take a long time. Performance is actually pretty good with this type of model. With our most recent code, we can reconstruct the state of a participant entity in a few milliseconds, and this is reading thousands of participant events. But there's a better way. This is not what we're saying. There's a better way. Snapshotting alleviates this problem greatly. A snapshot, as the name implies, is a special type of event that has all the state of the entity at that moment, along with a map of the last event that made into it. Now what we can do is start by loading the last snapshot for a given entity and then applying only the subsequent events, and this is much faster. So we don't have to actually load thousands of events. If we have frequent snapshots, we load a snapshot and then everything that's after that snapshot. Ideally, and depending on how we tune the system, that's not a lot of events, and that's pretty fast. This ability allows us to use caching mechanisms that don't have to be bulletproof. Even if slightly slower, we can always reconstruct the state from event. So we can survive without a cache. That's obviously not desired, but the impact that it has in resiliency and availability is significant, because when cache comes back, we can just keep on working. In the case of participants, we have a stable partitioning mechanism that promotes instance affinity. So we can keep the state in memory for even faster processing. There's going to be more details. This is important, an important aspect. Snapshot also alleviates us from having to keep all events forever in the active system. Events older than a couple of weeks, for example, can be discarded. Because we create frequent snapshots and keep the last snapshot for a given entity forever, along with all posterior events, we never lose any data. Today, we're storing this in Kafka, which is highly redundant and highly available, which is a good guarantee. Of course, there's a component in this system that systematically is archiving all events to an offline storage. So we don't want to lose all of the events just because we don't want to load them all every time we want the state of an entity. So for that, we have another component that simply is listening to all events that happen in the system and putting them in a safe place so that we can use them later. Of course, this can be used to, for example, provide a full backup. It can also be handy in more occasions than the typical disaster where we need to recover from that backup. But we also can do forensic analysis or even train a new AI model. And this is really important because not all designs allow us to have the full event chain or sequence of everything that happened in the system since the beginning of time. With this mechanism, we have that ability. And this is significant if we need to, a few years later, train an AI model or understand exactly how our system behaves in a certain situation, or even a more pragmatic and practical thing, debug a system and understand exactly what happened from one moment to the other, because we can reconstruct the state of a system up to that point. What this also allows us is to have a hot spare cluster in a separate region, because we can now ship all of those state events to the other side, to another cluster that's not being used, but it's being constantly updated with these events, which means that later on, if we have another disaster, we can switch the needle, we can switch a load balancer to the other region cluster, and that other region cluster has all of the data that the active cluster had with very little delay. This is not all perfect. Event sourcing doesn't address the complex querying problem. It's not going to be feasible to go to the event store and filter stuff or do aggregate queries. That's not going to happen. There's another pattern that's commonly used with event sourcing. That's CQRS, or Command Query Responsibility Segregation. It essentially prescribes a separation between the parts of the application where the business logic is executed and consequent state changes happen, from the parts of the application where the data is served from, but not changed. It starts by making peace with the fact, and I quote, "A single model to represent data cannot be appropriate for reporting, searching, and transactional behavior." These are the famous words from Greg Young back in 2008. And a lot of us have been struggling to make that single model work for everything. Most of us failing one way or the other. It's just not easy. A model that allows fast writes is not the best one to allow fast reads or aggregate reads. If we then compromise on the other side, enabling fast reads, we end up having locks or more locks and decrease the performance on the right side. So there is no perfect world, and this pattern recognizes that. With CQRS, we can have as many projections as we want, operational, audit, aggregated numbers. And the projections, to be clear, are the multiple views or the multiple data stores that we can have on the read side. We can even add more projections later on. All we have to do is replay the events that I mentioned to feed those new projections. We can use the right technology for the job and not necessarily relational databases for everything. For example, we can have a Neo4j graph database, an Elasticsearch for fast searches, or InfluxDB for time series. All of these data stores will provide different read needs from exactly the same events that are being published by the right side. So this comes at almost no cost. So to recap, on the right side, we don't need complex queries, we only need the latest state of a given entity. So there's no problem there. We can now have as many read side projections as we want and serve as many queries as we want without affecting the right side performance. This is also very important. This decoupling makes it so that we can load the read side without impacting the right side, and vice versa. This is why CQRS with event sourcing is such a popular combination in large-scale distributed systems. So you can see here that the way it works. The events on the right side are the events that are being published over time, and on the left side, on the right side, which is at the left of your slide, we have the events that are being published. On the right side, which is the read side, sorry, this is confusing, you have what's happening on a database that's being fed from the events from the left side. And we can see that this is happening asynchronously. So reads don't affect the right side performance. This is a built-in or free audit log. We can have as many projections as we want, as I mentioned. This is a big benefit in terms of performance and extensibility. So onto the typical integration mechanisms and styles. Sharing databases is, as we know, the highest form of coupling. We're tying everything together at the level of data. Imagine the effort to change a database and not knowing how many of the tens of services use that database. So it is not trivial. It's actually quite difficult to do that. And we tend to ignore the fact that systems will change, which is quite interesting because we make a living on changing systems and designing them, but we keep forgetting that systems change. So we need to make it as possible, as good as possible, so that we can enable change. And sharing databases is one of the worst ways of doing this. So this that I'm showing here is the typical model where the external system interacts with platforms through the APIs, where the external system is sending requests and receiving response from the API. And if it has an asynchronous mechanism, it even can receive some notifications over some whatever channel, HTTP or WebSockets. We can think of the API on our side as the current ML API adapter, or any future adapter that can talk, for example, gRPC instead of HTTP, or an entirely different format like ISO. And I don't know the number, it's 20, where I can never remember that. So there's a better way to do these integrations. This one is much better and faster. This is the streaming consumer, where external systems consume a stream of events from our platform. They do whatever they need to do with that data, and then they interact with the platform via the API when they need. This interaction can be to provide computed data, request an action to be executed, or even request data or more data based on some signal that it got. A good example of this integration could be a fraud management or an AI detection mechanism, where you're basically interested in ingesting all of the events that happen in the Mojaloop platform, and then doing some calculations, scoring, and making decisions, and then communicating back the decisions with the results to the API, where the platform can update wherever state it needs to update for the next calls. So this is a better way of doing the integrations. It's not that those two, one is bad, the other one is good. It's that this one is faster and has a less of a burden on our resources. Okay, so we come to this place. Not everything can be good. There's disadvantages. These two are the only significant drawbacks that we can honestly find. This architecture is obviously more complex, and it is not as intuitive as the typical client service or database sharing architectures, or even the simpler microservices architectures. It just isn't. There's a bit of complexity to it. The good news is that once we start using this sort of architecture, it actually becomes quite intuitive. So the lack of intuitiveness at the beginning is actually something that is based on what we're used to. And after being exposed to this, we start appreciating the ability to do things asynchronously, truly asynchronously everywhere. And we start embracing this. So it goes away. The complexity, though, won't go away. But on the complexity side, there's good news. If you look at the whole system, it appears to be more complex. In reality, the interactions of the system are more complex. What we don't see is that all of the individual parts are actually a lot simpler. And this is fundamental. This is really important. Everything that we have in our services, everything that we have in the valuable code is a lot more simple because they do just one thing and they do one thing really well. And we don't spread the business logic over different parts. We don't contaminate the business logic with concerns like technicalities of how to listen to an event and that kind of stuff. We don't do any of that. We are putting all of the gold, all of the good code, the domain code in the command processors that have no idea what's going around them. They are truly isolated and we can truly test them. So obviously there's a lot of advantages to this architecture. Besides the scalability and performance, the main advantages are that we have a fully encapsulated domain code that only exposes behavior. This enables testing and it makes it really easy. We have loosely coupled components that scale and evolve independently. And the evolution here is in the true sense of how systems change, how systems evolve over time. We have a separation between the execution logic and the queries, which can be optimized independently using fit-for-purpose and best-of-breed technologies. This is important to decrease the tie-in. We have also a highly available system where we can distribute this design across data centers or even regions, and this is important. There are more or less catchy advantages, like the write consistency at speed. And I know what some of you think, but despite the fact that the read side is eventually consistent, we only use it for external reads. And the write consistency is there. We lose no data. It's great for traceability. We have that ability to have multiple projections that don't affect the transaction speed. We are applying domain-driven design to make the business flow visible in the code. We can show this later if you want to see. But the curious thing is that when you look at the overall flow, you can actually see it translated in the code. The names that we use, the lines of code show the flow, the business flow. This is really easy and facilitates the communication between us technicians, product, requirements, and the client. We have simple code services, as I mentioned, that makes it easy to change with not a lot of magic. There's no magic. Everything is pretty simple. And the critical path relies only on Kafka, which is enormously scalable and performant. But we can adapt this to use other streaming platforms if necessary, like Microsoft Azure Event Bus or any other platform that allows the kind of streaming that Kafka does. And there are some others. Kafka is just, we think, the best. So the good news is that we already have the central ledger built like this. And all we need now is to make it production ready. We have a lot more info on the patterns and principles used in this POC. So to know a bit more, please check our report document that we will, for which we send the link here, and we have at the end. Well, with this, I'll hand it to Miguel to update you on the most recent progress. Take it away, Miguel.
Thanks, Pedro. So we started this in PI 10. So as Pedro said, that was more than 3 PIs ago. And we set out a couple of objectives, and we've achieved most of the objectives since PI 10. We have now an event-driven event sourcing and CQRS design working and tested in the POC implementation, which is anyone can access. You can download it, you can run it yourself. There's a link at the end where the code sits. And we've achieved a target of 5,000 transactions per second. Actually, we've done better than that. We've achieved just over 6,000 financial transactions per second. And once again, you can see the detail in the report on how that was achieved. Pedro also mentioned that a draft version of the report was also released, and there's already been a first round of reviews and comments. And of course, anyone can still go and add your comments or views onto that. There's obviously the Discourse community link that's been provided. Please use that. So the last point here is pretty much about production-ready feasibility study. And this was added in the last PI as an objective. And we've started this. The POC was designed with a happy path in mind. And that means that making the system production ready will require work on failure modes, adding tests, and improving the monitoring capabilities. Some of this work has been started, and we must continue in future if we wish to adopt this architecture. Can you go to the next slide, Pedro? So what was actually done in PI 12? Well, as mentioned, we've got the POC report that was produced and published. What we discussed during the last convening breakout session was a plan to make the POC much closer to production ready. This plan required a full team and a full PI. Unfortunately, we couldn't gather the required resources and start immediately after the convening. As a result, we only managed to start on the 1st of December with some limited resources, and we continued to work on this objective, like working on the snapshots and the separation of participant and account entities, etc., that we identified. But a few weeks back, we actually shifted our efforts to look at a more practical problem that could be solved within a time and resource constraint. And that really was, how can we minimize the hardware usage to help facilitate the adoption? And to this end, we worked on the required changes to enable batching, as we believe this would reduce hardware usage to this end. And also, we did some testing to understand how this architecture scales down. Next slide, Pedro. So what you see here is pretty much a result of this effort. On the bottom left, you can see we have the cost scaling unit. And this is the baseline we produced in PI 11. And there's more information about that in the documentation, but this is the report, but this is the minimum application infrastructure configuration required for a self-hosted environment to achieve around 1,000 financial transactions per second. And those are end-to-end transactions. That's including the full transfer prepare and the fulfillment that comes back as a result of a transfer itself. The backend stores were deployed with a minimum of 3 to 5 way clusters, with Redis being 3 and Kafka being 5. And we also, this provided partitioning and resilience capabilities for those backend stores. The services and backends were separated on optimized hardware. So we had specific IO optimized hardware, for example, for Kafka. We had memory optimized hardware, for Redis, and we had memory optimized hardware for Kafka. And we also had CPU optimized hardware for actually running our microservices themselves. As part of the batching, in the middle, you can see that we have taken the cost scaling units, we've applied the batching that we implemented, and we started reducing some of their hardware down to see what improvements could be achieved from that. So it's the same deployment topology as the CSU, with the same service and backend stores separated on optimized hardware. The only difference is there is a reduction in general computing workers, which actually resulted from a reduction of 7 to 4 nodes on AWS. And this actually resulted in, you can see the figures just above the boxes. Initially on the baseline, we had 46 CPUs, Now on the reduced CSU with batching, we only needed 34 CPUs to achieve the same 1,000 financial transactions per second. So what's really great here, you can see that we basically reduced the hardware by around 30%. One of the outcomes of introducing batching, though, is we've also increased the latency. But I think the latency is actually still fairly good. We had 75 in the original CSU, and now we've just increased about 50% to 147. That is still very much an acceptable bounds, and I still think it's a great response time. And of course, taking into consideration the other core target that we wanted to achieve, where after an hour run, we wanted to ensure that 1% of the transactions were below 1 second, we still achieve this very successfully within this topology itself. The last one is basically trying to run a lab, a simple cluster, right, which we could expect from a simple lab or development environment that is very cheap to operate. The services in the backends are deployed on the same shared nodes with the cluster. The backend stores are also deployed with a three-way cluster for both Kafka and Redis, and providing some partitioning and some resilience capabilities as well. But the idea is to make a very simple, very quick, very cheap way to deploy the POC or Mojaloop per se. And you can see here we've still achieved relatively good performance. We've got 250 transactions per second. The hardware has been now reduced by more than 50%. The latencies have gone up still by a considerable amount, by nearly 400% compared to the CSU. But once again, we're still within the percentage of transfers taking less than a second, being 1%. Can you go next slide? Then additionally, we also try to run this on something a bit cheaper, like my local development PC, which is a MacBook Pro 16, with a 2019 model with 8 cores. And prior to the batch implementation, I was only able to achieve around 25 financial transactions per second, which wasn't particularly very great. But by implementing this batch, I was able to achieve nearly a 500% improvement of 150, which is a great result, I think, for only an 8-core little laptop. Of course, the latencies are considerably higher, but I think that is fairly reasonable for something or the purpose of a local development environment. And of course, this was set up using Docker Compose. Next slide, please, Pedro. So we normally talk about how we can improve things on the POC. So you've seen some of these points before. So we've talked about in the past doing batch processing. We've done that, but we can further improve the batch processing. And the idea being is by implementing some of the other enhancements here, specifically point 2 and 3, we believe that would improve, well, those alone would improve the performance of the system and the scalability, but it would also impact and exacerbate the performance improvement that we would expect to see in batching. And the second point is specifically about separation of participant metadata and account and endpoint information. So at the moment, when we have a change to a participant, a position change, an update to an account, we are currently updating a single object that represents that participant. So by separating that participant out into individual entities, we are able to then basically update and persist much smaller data representations. And of course, this means that we're saving less data into Redis, and this means the messages that we're producing on Kafka will also be smaller. Then the third point is about the encoding and parsing of the messages that we're processing through Kafka. So at the moment, everything is basically JSON text, and by implementing something or adopting something like protobuf and Avro, we would potentially see quite a big difference here. And what are those things? Well, basically they're data serialization systems which marshals the data and schemas to a more efficient binary format. So the parsing and encoding of messages will be much more improved, and we would again most likely see a huge improvement on the batch processing as a result of that. The fourth item, and this is actually has a dependency on the second, where we need to separate out the entities from participants, the accounts, etc., is basically parallelizing the way that we process position changes or updates to accounts. So as I said, at the moment, we have a single participant. By separating those out into their individual entities, and we have a specific account entity, now what we can do is we can start sharding or partitioning those accounts. And that means we can basically parallelize the processing and provide a much more scalable and performant system as a result of that. The fifth point here is about using a faster language, like Pedro mentioned. Potentially something like on the command handlers, Java could be considered. It's definitely an option. It's something maybe that could be considered in future. And the final point here is about Tiger Beetle. You'll hear more about that, I think, after this presentation. I'm very interested to see how we can take advantage of that and how the POC can be modified to take, to see how they can impact the performance of the POC itself. Next slide. So in conclusion, so we've produced a scalability report. This report, we believe, shows that the proposed architecture is feasible, right? So a lot of work's gone into the happy path, but as previously said, we still need to go and work on some of the productionizing of the failure modes. And the POC can also run in parallel in existing Mojaloop platform components. So the idea being, and this is actually, there's a section in the report that talks about it, but the question is, can you run the current ledger? This POC, is it compatible with running with the existing Mojaloop components? And yes, it is. And as Pedro said, we are able to create materialized views and have a specific materialized view to keep the POC in sync with the existing databases that the account lookup service, the quoting service, and the central settlement services are dependent on. So in essence, we are able to run the POC in unison with those existing components with minimal impact. And another one that's also talked about in the POC report is about upgrading and migration of existing systems. Are they possible? Yes, it is, but we would need some support from existing implementers and hub operators to really make sure that that is 100% solid. We do talk about that in the report as well, and we do cover that. The other main point here is about the design is stable. We need to get the rest of the code production ready, as we mentioned before. We've traditionally haven't had not enough dedicated resources to do this, and this is something we would definitely like to have going forward. And the final point here is the POC is performant and it is scalable across multiple topologies. In this example on the previous slides, I showed some results that was in AWS in the cloud. I showed some results that was on my laptop. And of course, because we're using Kubernetes, there's nothing stopping you from running this on-prem. And in fact, I would imagine on-prem, you should even get better performance purely because you are able to control your hardware in terms of how it's deployed. Where on cloud, obviously, a lot of the time you're on shared infrastructure. So there's no reason why you couldn't. And of course, just adding on to that, we obviously deploying all the backend services, Redis, Kafka, MongoDB, as part of the deployment, as part of the POC on our own Kubernetes infrastructure. There is no reason why you can't use a self-hosted or managed service for any of those. If you want to use a cloud-provided hosting solution for those, you can. If you want to use your own, you can. If you want to use the ones that we're packaging as part of the POC and deploying in Kubernetes, you can. Thanks, Pedro.
All right. So to recap, what are our conclusions? Well, sorry. Separating different tasks and responsibilities, as well as the data stores, delivers the desired horizontal scalability. That separation of transfers and participants provides data store partitioning without the extra effort. As Miguel mentioned, there's an even extra benefit that we can have by separating the participant into position plus the metadata of the participant. We have code and integration examples for the settlements. The event-driven CQRS and event sourcing design effectively shifts the load to Kafka, which is very efficient at scaling horizontally, even with the replication, and this is something that we considered. It's actually faster than the current design, and it has shorter response times per transaction. So I see you guys commenting about the latency. It is true that the batching mode that we have put in place in this PI increases the latency, but it increases from 75 milliseconds to 150 milliseconds, which is still a lot faster than the 1 second limit that we have. So we're well below the limits. And this is the way it is. Batching sacrifices latency. It is how it is. That's why we need to have a right balance for the right load that we have. Most importantly, we have produced a central ledger design that is faster, handles a lot more load, and is cheaper. So it's also retrofittable to the existing deployments that we have. Obviously, there's a lot of work to do that migration, but it is retrofittable, and that was one of the objectives. So it's almost 9 months since we started this. We started slow, managed to achieve great results, and are now again in a slower phase. The initial ask was scalability and performance. We aimed to deliver it in a sustainable way with an eye to the future, obviously not forgetting about the cost. Now, we are aware that the marketing position challenges we face, they are more important than the pure performance numbers, no doubt about that. The reality is that we now have designed, POC'd, and documented an architecture that scales in a conscious way. It doesn't depend on a single technology, everything can be replaced, and it is modular, with a focus on integration and extensibility to enable a marketplace. Obviously, we believe that these are the characteristics of a great platform, and we would like to start the discussion of what a future architecture for Mojaloop looks like. Of course, we think this should be it, but we're biased. That's it from our side. I see that there's tons of questions, so happy to answer them.
I see. I see a question from Miller. He mentions if batch size is tunable, the latency throughput trade-off could be adjusted. Yes, you're 100% correct. As we increase the batch size, the latency also increases. So, we did several tests where we would change the batch size to see what was the optimum value based on whether we're running on a laptop, whether we're running on AWS, whether we're running on the 3-node cluster. We basically were able to do several tests to determine more or less what was the best or acceptable latency with a high throughput. I imagine that's very much going to be based on your target environment.
We have a few minutes left in the session. I'll see if we can take just one question. Anyone else wants to maybe vocalize a question? Leslian asks, any analysis on timelines to get it completed?
Well, that's a good question. Last time around, during the last convening, the last thing that we did during those breakout sessions was list all of the activities that we needed to execute to deliver the production ready. Obviously, that needed a full team, and it needed a full PI of time. We unfortunately couldn't have enough resources. It was basically me and Miguel, and not fully dedicated to this, so we did what we could. We also didn't start at time, and then there was Christmas. So we still have that. I think this goes to the question that Miller was asking. We still have that list. We know exactly what we need to do to make it production ready. And we think that we know, at least from our planning and resourcing, exactly how much resources we need and how much time. So we have this idea that we can deliver all of the production ready aspects in one PI with the team that we are requiring.
Just one quick one from Dave Spooner. So he asks, in a real world use case, how many transactions are likely to be applicable for batch processing? And you're basically asking whether this is internal batching within the switch, or is this a specific type of transaction? So this is internal batching within the switch. So basically those messages are flowing into Kafka. one at a time from a DFSP, and we're utilizing the Kafka mechanisms to be able to pick up several messages at once, pull them into memory, process them in a chunk. And in fact, even when we, for example, write the results out to Redis, we would also take those batch of messages and write them as a batch operation into Redis itself. So we're optimizing not just how we are processing the message through Kafka, but we're even optimizing how we're writing those to the stores. And you also ask about, is the latency from an end-to-end perspective simulated from a DFSP usage? Yes, it is. So it's basically from sending a message from ML API and theoretically receiving that from a notification. Although we didn't include the notification through HTTP, we just pick up the final notification that was published onto Kafka, which is the same way that we tested as part of the report. So we use the same methodology.
Miguel, I was going to kind of add that I think in a lot of situations with batching, when we look at just a level of performance that a deployer would be, trying to hit, or on a day when they're being asked to hit something they don't normally experience, you think there's a baseline increase to latency with batching, and as you pointed out, it's still a very good number, and it's a cost tuning tool. I think with batching though, you limit the impact on the other side, because you're able to be more efficient with resources when resources are constrained. So I'm sure that we haven't been able to do a whole lot of exhaustive testing there, but there's probably a lot of better cases where at a given level of performance, when the system is stretched a bit, batching actually reduces latency, or the latency of what some people would experience. Again, you can't average latency because some people are having a great time and some people are having a terrible time. But I think that it would be less people having terrible times in a batch scenario when the system is really under load.
Yeah.
A quick one from Miller about how do we control the batching, and I think the question was how do we avoid that the batching steps up and is the most important thing. We have a mechanism where we say we would like to get 500 messages or 220 messages, or wait for 100 milliseconds. Whatever event comes first is when we take whatever we have and process it. So we don't wait more than 100 milliseconds, and we maximize the ability to get as many messages as we can within that timeout. So this is something that the Kafka consumer provides to us, and we're taking full advantage of. This enables us to have that control over the latency. Batching makes it go up, but we can control. We can say it will not go above a certain number. So this is an important aspect. That's a great question.
Can I just ask a question about the latency figures, guys? You said, Miguel, that you didn't test with the HTTP callbacks. How does that compare to how we tested the existing, I suppose we could call it even now, legacy architecture? Those were making HTTP callbacks to simulators, weren't they? So the latency you quoted is just through the command handlers, right?
So if you go back to the characterization that we did several tests where we removed the HTTP portion of the notifications out to see what the impact was. So if you actually go back to the reports that we did, you'll see that we actually did that, and we tried to understand what is the impact of the notifications. And one of the outcomes of that investigation was we identified there needs to be work on the notification handler to improve its performance. And I think there was a discussion in terms of that was out of the scope of what we were trying to do here from a central ledger perspective. And I think Brian actually was the one who suggested that that should be its own stream. So as part of that, when we started doing the work in PI 11 to basically characterize this POC, we didn't include that purely just so to be consistent and to make sure that wasn't impacting the results. And
but then the latency numbers we can't compare across the two sets of test results, right? Because the latency has been measured in a different way. So we can't look at the old one and compare that latency to what you've achieved here, and
you can't
be a comparison, right?
You can somewhat, in the way those numbers were reported, if they were posting out to with the, to a remote simulator and getting a thing back, that latency was subtracted out. But in the best case scenarios, when we were talking about the performance of the real-time components, if you will, the position management and transaction updating components, I believe at the end of that, the notification handler was essentially posting straight back to the Kafka topic on the receiving side. And we were taking out all of that latency. So, there's not a case where the existing is running better, if that's what you're thinking, because it was doing more work. We stripped away all of that because it was noise. It's very hard to tune receiving transfers when you're waiting on something that's out of your control, like a pair of HTTP calls and a simulator, to basically be the source of your load.
Yeah, okay. I just have a concern, though, that if we want to be able to compare one against the other, we have to test them in exactly the same way and measure exactly the same points. Well,
I don't know that we need to. This is my opinion. I don't know that we need to compare one against the other. I don't know if it's a bake-off in that situation. I think that we can evaluate the design merits of this particular approach on its own and say, do we see where it, A, either scales well, or B, reduces the load on the system or better positions the system to deal with changes in data patterns efficiently. And then if it's a good pattern, move with it. The other mode had, that was not a complete design either, and that it just all depends on the database going faster and faster and faster. So I think most of what Miguel's talking about is things that we would have naturally done on that code path anyway.
Sorry, guys. I want to jump in here and say we're 2 minutes off our time. Can I ask that we move this conversation to discourse or perhaps schedule another call to go in deeper? Brian, James?
Absolutely.
Cool. Miguel, I'll pass it to you to wrap up.
I think we're done. I don't know, Pedro?
Yeah, we're done. Thank you, everyone.
Thanks, guys. Thank you very much.
Awesome. Thank you so much.